In this lesson, we're going to figure out how to do a significance or a hypothesis test for the difference of two proportions. So let's understand this with an example. My question at the top, which grade is more likely to go to prom, immediately signals in my mind that I'm talking about two different populations here. So I know I'm going to be doing a test for the difference of two proportions. Okay, the student council at a large high school is wondering if juniors or seniors are more likely to attend prom. They take a random sample of 50 juniors and find that 28 are planning on attending, and a random sample of 45 seniors and see that 29 are planning on attending. Do the data provide convincing evidence that a higher proportion of seniors are going to prom than juniors, and we are to use an alpha of 5%? So I'm just looking at my statistic here just to kind of comprehend this. My statistic is showing that I have a difference, okay, in each of my samples. So the sample proportion of seniors is 29 out of 45, which is, I believe, 64%. Minus 28 out of 50 is going to be 56%. So I have an observed difference that 8% more seniors are going in my sample. But of course, I've got to see, is this observed difference great enough to conclude that there's really a difference in the population? So we're going to do a significance test. So let's do our state plan do conclude. So let's begin by we want to test. And I'm going to state my null and my alternative. Okay, there's two ways of doing your null and your alternative. Both ways, make sure you are always using parameters, so no p-hats in your null. So I'm going to do, if there, my null would be that there is no difference. It's my status quo. And then my alternative is what I have a suspicion about. So one way of writing this is, I'm going to use the subscript of senior. The proportion of seniors minus the proportion of juniors is 0, that there is no difference. The way I like a little better, you're going to see it more often in this course, would be proportion of seniors then would be equal to the proportion of juniors. You know, just imagine adding P of J to both sides here. Again, the alternative then, one way is that the difference would be greater than 0 because the proportion of seniors being greater. Using this, I prefer this notation. We have to define our parameter and state our alpha level. So where P sub S is the true proportion of seniors attending prom and P sub J is the true proportion of juniors attending prom at this large high school using an alpha level of 0.05. So we're ready to go on to the plan portion of our significance test. This is where you need to state your test. I'll begin like that. So I have, if conditions are met, we will conduct a 2-sample Z test for P sub S minus P sub J. Just on a side note, also called a 2-proportion Z test. So we're going to move into our conditions. And our first condition of random is the same as it was for confidence intervals for the difference of two proportions. But with random, this is the one where we need to say that we have independent random samples. So I'm stating that I have independent random samples of 50 juniors and 45 seniors. Now my 10% condition, I have to address the 10% for both samples. So I say that 50 is less than 10% of all juniors at this high school. Of course, I'd be doing a little bit of assuming there. And 45 is less than 10% of all seniors at this high school. Now, our large counts condition is where we're about to run into something a little bit different. And this difference comes from the idea that remember in significance tests, we're always doing everything based on the assumption that our null is true. So if we're saying that the proportion of seniors is equal to the proportion of juniors, and then I go to the large counts and I end up using different values for the proportion of seniors and the proportion of juniors, it doesn't really make any sense. So we do this idea of where we combine our data. It's also sometimes called pooling our data. Like the idea, throw all your seniors and all your juniors in one pool, combine them and find what proportion you have. We call this our p-hat combined. So I typically do this right here. I calculate what p-hat combined is. And what you do is you put the total successes in each group. So from the beginning here, it was 28 out of 50 juniors. And we're going to add these two together, kind of like find your average. And 29 out of 45. So we have a total of 95 people like combined. So 57 would be the sum going to prom. So 60% is our combined proportion going to prom. You think of it like a weighted average of your sample proportions. It's if we are again expecting that these are equal, we're not going to use different values to calculate our expected counts. So normally in our large counts, we do our sample size times our P, null P if it's a significance test, our p-hat if it's an interval, but here we're going to use our p-hat combined. So I'm going to calculate my expected number of juniors, seniors, because I use the subscript S. So the number of seniors there was 45 in our sample, so how many would we expect to be going? We're going to multiply that by 0.60, and that gives me 30. No, it doesn't. Excuse me, that gives me 27. And then the complement, the number of seniors times 1 minus p-hat combined would be 45 times 0.4, which is 18. So our expected count of seniors going and not going to prom are both greater than or equal to 10. And then I need to do this for my juniors. So the number of juniors times p-hat combined would be 50 in my sample times 0.6. That's 30 that I would expect to be going to prom. Sample size of juniors times p-hat combined, times 1 minus p-hat combined. The complement is 50 times 0.4, so that's equal to 20. So altogether, all of these are greater than or equal to 10, which is what they need to be in order to meet my large counts condition. So I'm just going to say conditions met. Okay, so I've kind of zoomed out. I've made this first part small, so it's going to be a little bit out of perspective here as I go on to the do portion, but I wanted to be able to still reference it even though it's tiny if need be. So for our do portion of this, I'm going to get my standardized test statistic. I am doing a z-test, so that means I want my z-score. And a z-score is equal to your statistic minus your parameter. So our statistic, z-score is statistic minus parameter over the standard deviation or the standard error of the statistic. That general formula is on your formula sheet for the AP exam. So our statistic, we actually did that at the very beginning. We found it to be 0.08. Minus our mean. or a parameter? Well, we're assuming that they're equal to each other or that there is no difference. So it is 0 over the standard error. Now, you might be tempted to go back and use different values for like our proportion of juniors and our proportion of seniors. But again, you are going to use your combined p hat. So I'm just going to show you here what the formula is. So you're using this formula over here. Please pause the video if you have not found this on your formula sheet yet. Okay, so don't be tempted to accidentally plug in different proportions like your sample ones for seniors and juniors, because in a significance test, you're assuming they're the same. So you're going to use your p hat combined, which we've already calculated to be 0.6. So it's going to be 0.6 times 0.4 over, over the number of seniors and then one with the number of juniors. So one of them can be 45 and the other can be 50. So again, 0.6 times 0.4, because we're using a pooled or combined proportions. And this is going to give us our z-score. So my z-score is, take a second, please type that in your calculator. I get 0.79. Now, as I do this, I don't normally have all this explanation of a z-score. I just jump right here to my z-score as long as I have my p hat combined somewhere, and up here I had my statistic. I also always draw my normal curve. It gives me direction. So I'm going to go approximately normal, and I'm going to do standard normal, 0 and 1, 0 in the middle, 1, 2, 3 standard deviations in either direction, and 0.79 or more extreme. So my p-value is going to be the probability that my z is greater than or equal to 0.79. And if you go and do normal CDF, 0.79, upper is 9999, 0 and 1, and don't just write it like that. Make sure you have lower, upper, mu, and sigma. Everything's labeled. I get a p-value of 0.215. That's a pretty high p-value. So that's telling me it's not very rare. So I am going to fail to reject in my conclusions. Let's go on to our conclusion. I always begin by comparing my p-value to my alpha level. I say because the p-value 0.215 is greater than alpha equals 0.05, comma, we fail to reject the null. And then I state, we do not have convincing evidence for the alternative that a greater, and I'm going to make sure I'm talking about my population, that a greater proportion of seniors go to prom than juniors. Okay, so this is very sloppy. You have to kind of move the video back and forth if you need to see the state plan do conclude portion. Just big idea is that you get this p hat combined down pat and recognize that you use it when you are assuming that there is no difference in your population proportions in your hypothesis.